So now we're going to use vector methods to prove Pythagoras' theorem. Let's start, as usual, by drawing a diagram. Here I need a right angle triangle. Oops, that's a right angle. That didn't look like a right angle sign, did it? Right angle. Now, I'm going to label these sides as vectors. This one's A, this one going upwards is B, and this one over here is C. So there are two results I need before I can start this proof. The first is simply to note that C is A plus B. Okay? To go from here to here is the same as going here first and then there. And I'm actually going to need this in terms of one of the other sides. So I'm going to say B is C minus A. Okay, we're going to come back to that later. Another thing we're going to want is this. These two sides are at right angles, and we're going to need that result. So, A dot B must be 0. Remember, that's how we say that they're at right angles using vectors. Their dot product is 0. But B is C minus A. So that's the same as A dot C minus A. What I've done is replace B with something that's equal to B, C minus A. If you're a bit stuck vector-wise, to go this way is the same as going C minus A. That'll give me this vector, same as B. Okay? All right. If A dot B is 0, because they're at right angles, then A dot C minus A must also be 0. But this, if I expand it, is A dot C minus A dot A, which means these two are equal. A dot A must equal A dot C. And that's going to be important later. Okay, let's start the proof proper. What I'm going to do is take this same side that I wrote by itself, and I'm going to work out its dot product with itself. I'm going to say, what is B dot B? I want the dot product of B with itself. And I'm going to replace both of these B's with the same C minus A. C minus A dot C minus A. Well, let's expand the brackets. That's C dot C firsts. Outside is C dot A minus C dot A. Inside is A dot C minus A dot C. And the last is A dot A, and it will be plus two negatives. Plus A dot A. Well, what does that tell us? Notice C dot A and A dot C are actually the same thing. The dot product is commutative. It doesn't matter what order you write it in. So I've got C dot C minus two lots of A dot C plus A dot A. Now we're going to go back to this result from before. A dot C is the same as A dot A. So I've got C dot C minus two lots of A dot A plus A dot A. Well, I've got minus 2A dot A plus A dot A means I've got C dot C minus one lot of A dot A. Now, I hope by now you can see where we're going. What is B dot B? Well, it's just the length of that side vector B squared. And what's C dot C? Well, it's the length of that vector C squared. And what's A dot A? That's the length of this vector A squared. And this is Pythagoras' theorem. The square of the hypotenuse is equal to the sum of the squares of the other two sides. If you prefer, you could write it that way. You could go mod A squared plus mod B squared equals mod C squared. And I have proven Pythagoras' theorem. So I've proven what I wanted, QED.